Hello Internet, my name is Quinn, and this is Blondihacks. This is the final part on the knurling tool build series. We're going to finish this thing, we're going to try it out, and we're going to make some little improvements along the way. So let's go. Here's where we left off last time, a nice pile of parts, but we've got quite a few more to make before this will be a knurling tool. So let's get going. I'm going to start with a couple of really boring hinge parts that have no interesting operations on them. I'm just kidding, I'm not going to make you watch. There's the hinges. They just have threaded holes in each end. And just for good measure, I bumped the camera in the punchline on that joke. This is the kind of quality content that I know you're here for. Now I'm actually going to start with an interesting part. This is sort of the lead screw of the knurling tool. It's a big threaded rod that clamps everything together. You can see I've got a lot of run out in that part after clamping it in the collet chuck. And well, that's mostly because these are really cheap collets. But don't fret if this happens to you, because you can tap in any fixture, even a collet chuck. A little bit of tapping there, and we're within a couple tenths of run out there. The trick is to tap close to the fixture, because if you tap at the end, it's just going to spring and you're not going to get anywhere. But just remember that any work holding method can be tapped in. Or by better collets, I guess. I'm not going to face the end, as would be tradition, because of the amount of stick out there. That would require setting up the steady rest, but I don't actually need to face the end, so I'm not going to bother. I'm just going to center drill it instead, because I'm going to need tail support to make these threads. Now I don't want a center in the end of the final part though, so what I'm going to be doing is leaving extra stock at this end so that this center can be faced off the end once we're done making the part. You'll see how that all fits together here. Now the first threaded section here is very long, and I could certainly do it with a die, but what the heck, let's single point cut it. I haven't done that in a little while, and this is a good use case for single point thread cutting. I'm going to start by creating a shoulder that defines a reference for the end of the part for real. In other words, how much I'm going to be cutting off later to get rid of that center there in the end. And this shoulder will be used as the reference for all the other features on the threaded rod here. I'm doing this with the parting blade. And now I can blue up the region where the other end of the thread is going to need to land so that I can mark from that reference shoulder where it's going to end up. And once in a while I do use my calipers for marking layout fluid like this. Mostly I use odd-like dividers when there's room, and now the 50 of you who are thinking about commenting about it don't need to. Centering on that line now, I'm using a round-nosed grooving tool to put a nice curved relief here at the end of the thread. It gives an entry point for the threading tool and is stronger than a square groove would be, because square grooves have rectangular corners in them which can create stress risers and eventually crack. At this point I realized instead of cutting a groove there, I should have actually just turned down the entire end of the part there, because I'm going to need to be able to pass a nut over that area in order to test fit my thread. So I turned that down, and I'm also going to turn down the main body of the thread here as well. This is precision ground drill rod or 01 tool steel that's been supplied in the kit, but you don't want to try and cut threads right at the nominal diameter of the thread. Threads need clearance around them. How much exactly you can look up in Machinery's Handbook, or you can just cut 2 to 5 thou off of it like I do. I always blue up the part that I'm going to thread also, because it helps see the scratch pass, and it helps you see when you're getting close to your final dimension, because you can see the blue start to turn into the peaks on the thread. And now, this being a low-budget hobby lathe, we do the change gear dance in order to get the correct thread pitch on the lead screw. Electronic lead screw, electronic lead screw, electronic lead screw. There, now the 50 of you who were going to comment on that don't need to. Do a little bit of a scratch pass here and check it with the thread pitch gauge to make sure that I've got all of my gears and the quick change gearbox set correctly for 24 threads per inch, and I do. And at this point I realized that I forgot to square up the tool with the fishtail gauge, so I'm doing that now. Single point thread cutting involves a lot of little setup steps, and it's very easy to forget one if you don't do it very often. I also have my compound set at 30 degrees here. Normally for a thread this shallow, I wouldn't bother using the compound, but this is tool steel and it's long, thin stock, so it's going to be hard cutting and prone to deflection. So I want to minimize tool pressure as much as possible, and that's what using the compound does for you when feeding for thread cutting. And as usual here, I'm running the lathe in reverse, and I have the thread cutting tool upside down so that I can thread away from the chuck. This is my preferred method, and it's a method that's covered in a lot of the really old school machining books. You don't see it a lot done nowadays, but it works great as long as your spindle isn't threaded, in which case the chuck would tend to unthread itself if you ran it in reverse like this. And when I think I'm getting close, according to the dial indicator that tells me how deep I've cut so far, then I start test fitting with a nut. And of course, you could use thread wires or thread mics or other fancy ways of measuring this, but I'm a sloppy hobbyist, so I test fit with a commercial nut. And that was close, but didn't quite thread on, so a couple more light cuts and a couple of spring passes. Spring passes are especially important on long, thin parts like this because there is going to be deflection near the center of the work. So the center of the thread, or in this case, the left end of the thread, the middle of the stock, is going to tend to be a little fatter if you don't do spring passes. So the nut might start okay, but then get tight towards the other end if you're not careful. I'm happy with that though, so I can now take this part out and flip it around because there also needs to be a short thread on the other end. Now normally this short thread I would just do with a die, but I mean, I got the change gears in there anyway, I'm all set up, I might as well single point this end also. This is exactly the same, it's just a shorter thread. I'm once again putting a little center in there and I'm going to leave extra stock at the end that'll get faced off. Do all the same setup with the groove and everything. In this case I'm referencing from the other end of the smooth section of the bar there. And then I cut that little thread at the end. You'll note that I did a number of turning and grooving operations there before doing the threading, and I didn't touch the change gears. You can still use the lathe normally with the threading gears in there, you just can't power feed. I mean, you could, but threading gears are effectively a very, very fast form of power feeding, so you wouldn't want to. But you can still feed by hand the way our grandparents did. With that thread done now, I can choke up on the part in order to face the center off there. And I can hold it by the threads there. That's one of the superpowers of collets, is that they can hold a thread like that without damaging anything, just because they squeeze nice and even all the way around. So a series of facing cuts removes the center there, and then I face it down to the thread, and I put a chamfer on the end of that because, of course, chamfers are what separate us from the animals. Then I flipped it around and did the same thing on the other end, and here's the final result. This is, again, what I'm calling the lead screw, if you will, of the knurling tool. I'm pretty pleased with how that turned out. I'll add that to the pile, and let's move on to some brass. There are two brass collars in this device that hold the ends of the compression spring for the tool. So I'm going to face off the end, as is tradition, and these collars are kind of a trumpet shape. They have like an inverted T, and then they're hollowed out in the middle in a shape that follows the T of the outer surface of the part. So surprisingly intricate and interesting to make. I start by drilling and reaming all the way down the center of the part for the smallest diameter. Then I need to counterbore to a very specific depth here on the front end of the part. So I've moved my boring bar clear after touching off, and I'm using an indicator to set the final depth. And then I can do a series of boring bar passes in to just a couple thou short of that final depth. In other words, I'm roughing in the counterbore here. This is the same process I use for turning an accurate shoulder with good surface finishes on both. Now you might be tempted to use a caliper here to measure this, but this is really going to be inaccurate for an internal bore, especially a small diameter one like this. So that'll give you a rough estimate, but really you got to go to the gauge pins to know where you're at for a small bore like this. So there's some trial and error to figure out which gauge pin is the closest fit without going over. Price is Right rules, and that'll tell you what your current diameter is. And then that allows me to dial in my finishing cut, which I do all the way into 0 on the indicator and then feed inward on the cross slide to finish the back face. And then I have proper dimension on both diameter and depth with good surface finishes. I'll do a final inspection here. So the gauge pin that is the size that I was aiming for is kind of a snug fit. Like it doesn't quite go all the way in. You could probably force it in, but it's really close. And then one size down goes all the way in and it's just a touch sloppy. So I know my final dimension is between those two sizes, so I'm within half a thou of the target dimension, which is well within tolerance. So I'm happy with that. And then I'll verify the depth with my depth mic here. The great thing about a counterbore feature like this is if my depth was too shallow, I could take another cut. If it's too deep, you can just face a little bit more off the front of the part. So if you need a really accurate counterbore depth on a part, try to arrange to do that counterbore first before you get committed to the length of the part, because then you can always adjust it by facing if you need to. Next, I'm going to turn the OD of the entire part to the largest diameter, which is kind of the top of the trumpet, if you will. I'm turning it with the wide part of the trumpet outboard away from the chuck, which is not how you would do it if you wanted to turn a nice shoulder, but I wanted to be able to do all the features here in one setup, so in order to get that counterbore, I had to do it this way. This diameter isn't super crucial, so of course I completely nailed that dimension. Now I find the edge of my grooving tool here on the end of the part, and then I use an indicator on the carriage to translate down to where the underside shoulder of the trumpet area is. While I'm here, I'm also going to mark the far end of the part so I know roughly how far to go down with the grooving tool here. Just like you've seen me do earlier on this project with an inside shoulder, I do a series of grooving operations to within finishing cut range of the final diameter. On the final cut, I pan across to even out the surface in case the grind on the tool isn't perfect. And I also went past my scribe line there to give room for the parting blade at the end. Then I check my diameter here to see how much I need for my finishing cut. And then I go in all the way to my finishing cut distance and pan across, and Bob's your uncle. The drawing calls for a nice chamfer on the underside of the trumpet here, which I can't argue with. It will look really nice, but this is a dangerous game because this is a pretty thin-walled part, so it would be very easy to go too far with that chamfer and break through on that inside corner there. So I went as far in as I dared and then set up the parting blade to part it off. While I'm in there, I'll break the sharp edge on that backside, and Yahtzee. Like so many parts on this project, I needed 2 of them, so I made 2 of them, both exactly the same method that you just saw. Next up is another brass part, the adjusting knob for the knurler. The kit gives you this little stub here. So if I put it in with 2 teeth on the jaws there engaged, I don't have enough length to create the part. And I don't want to try and do this with 1 tooth engaged because that's really asking for trouble. Now the kit suggests tapping and threading the center of the part and then mounting it on a mandrel in order to turn the remainder of the features so that you don't have to hold it in the chuck at all, and thus you can use this very short piece. I'm sure that would work just fine. However, it's a lot of fooling around, and I have longer pieces in my scrap bin, so I grabbed one of those. Like most brass knobs, this is a larger diameter with a smaller diameter shoulder under it, a threaded hole down the middle, and a knurled area on the large diameter that makes it into a thumb wheel. So I was all pleased with myself. I turned this all up very quickly, and then I realized that doesn't seem right proportionally. And it turns out I'd misread the drawing, and I'd made the outer diameter 5/8 instead of 7/8. So I got another piece of stock out of the scrap bin, and turned that up again, and now I'm back to where I should have been. Maybe if I just used the stock in the kit like I was supposed to, I would have been paying more attention. Who knows? In any case, I drilled and tapped that for the knob, and now we need to put the knurl on the outside. Now, wait a minute. If I had a knurling tool, I wouldn't need to be building a knurling tool right now. This is the classic chicken and knurler dilemma that every 5-year-old asks you about. I could cheat here and use my other knurling tool, but if you're buying this kit, there's a good chance you don't have another knurling tool, so where's the fun in that? Now, luckily, the kit has us covered here. So I'm going to do a partial assembly of the knurling tool with all the parts that we have so far, and we can use this proto-knurler, if you will, to actually do the knurling on that knob. After assembling all the arms, the knurl wheels go in, slide the axles in, and then these little set screws here hold those axles in place. And then the threaded rod assembly goes down the center here with those really cool half-round nut things that we saw earlier. And the collars are supposed to slide over the threaded rod section here, and they won't go. Now, why would that be? Well, this is actually a really common problem and why projects always need a little bit of fitment at the end. The reason is simple. This is precision ground threaded rod, and it happens to be dead nuts on size, 312.5 thou. That's exactly 5/16. And well, that's what we reamed the holes in those brass collars to. So oftentimes when you design things like this or in a kit like this, there's some assumption that the reamer is going to cut a little oversized and that the stock's going to be a little undersized, and so it'll probably fit. Well, in my case, the reamer cut right on size because it's a good reamer and I set it up carefully, and this precision ground stock happens to be right on size, which they typically vary more than that. So I had to take some emery paper to the round stock there to tune it down a little bit to where the collar would go through. If you have an oversized reamer you can run through the brass part, that would be a lot easier, but I didn't have one in the right size. And there wasn't a drill size close enough that I was comfortable running through there because they're pretty thin wall parts already. Now, it goes without saying, before you start modifying parts to make them fit, be absolutely sure everything is properly deburred. On close-fitting parts like this, even the tiniest burr or chip that you can't even see is enough to make them not fit the way your enthusiastic CAD drawing says they should. So with all of that sorted out and everything fitting together nicely, now we can install this nut here, and this nut comes in the kit specifically for this purpose, so that you can temporarily assemble the knurling tool and then use it to knurl the knob, which I think is quite a nice idea. Now, one thing I kind of don't like about this design is you can see that even with the nut tight, there's still some slop in the jaws, and that's because of how these brass collars work. There's a space there between the arm and the top surface of the bearing plates inside there. And that's necessary because if the arms are open very, very wide, there needs to be clearance for those collars on the insides of the arms. So I'm not sure if it could be avoided. I think I might just shorten those collars up a little bit so that this effect is less, because I'm mostly working with small diameters. Food for thought. It's not my favorite part of this design. Things are getting exciting now, though. We get to actually try this thing out. It's going to be cool. I clamped it into a tool holder there, and I'm going to get it on center. Now, being on center is not critical for a scissor knurler, so just getting down low and lining up the shank of the tool there with the center line of the spindle by eye is good enough. And then I can start tightening this down. Once you've got it tight enough to where both wheels are turning, indicating that both arms are fully in contact, then lots and lots of lubricant in there, and I can tighten this down 1/4 turn, and I can do the first actual knurling pass. I'm running at 100 RPM here, and I engage the power feed to do one pass down the area there that needs to be knurled. Then I can stop and check if I'm happy with that, and I want more depth than that, so I put another 1/4 turn on it, I reverse the power feed direction, and run it back the other way. You can keep doing this as much as you want. As long as you never disengage the knurl wheels, then they'll keep tracking in the same grooves that they've started. Just don't ever loosen them. Just keep tightening them and change the feed direction on your lathe to feed back and forth as much as necessary. This works better than trying to do the full depth knurl all in one cut. It's really asking a lot. Most knurl wheels like these are forming tools, so they're creating the knurl with pressure. They're actually plastically deforming the material. They're not cutting it. Now, cut knurlers do exist, but that's a whole separate topic. Most knurl wheels are going to be the pressure type, so you don't want to get carried away trying to do too much at once, and you need to use lots and lots of cutting fluid, as you saw. Getting ready to part this off now, but as I always say, the real secret to a good-looking knurl is a generous chamfer on both sides, so I'll do that while I'm here, and then finish parting it off. And Yahtzee. Now let's install that knob on there and see how it looks. And I think that looks very nice indeed. Now at a glance, that knurl looks pretty good, but something's a little bit off, as you may have noticed earlier. Let's take a look under the macro lens, which reveals all truth in machining. Now you can see that it formed nice pyramids. The sides of the diamonds are closed all the way up to a point, but the diamonds are not symmetrical. They're all lopsided. So why would that be? The knurl wheels in the kit are a fair bit narrower than the space in which they live, and you can see there's a fair bit of lateral play in them. And in fact, when you see me engage the knurl tool here initially, look at that lower knurl wheel. As soon as it engages, you see how it slides to the right? That's because of that end play on the shafts there. And because the flutes on the upper knurl wheel are angled the other way, one wheel is going to slide left and one is going to slide right, and thus they're going to become misaligned. So I think that's why we're getting lopsided diamonds. To fix that, I'm going to put some thrust washers in there to take up that space. So I measured the gap with a feeler gauge on each one, and I've got some aluminum bronze here, and I'm going to turn up some little thrust washers. So I slid the thrust washers in there on the same side of each wheel. And hopefully that'll force the two wheels to always ride in alignment with each other instead of sliding to opposite sides. So once again, I'll tighten that down until the wheels are both touching. So I'm going to do the same test as I did before so we can compare. All cutting conditions are the same here, same diameter stock, etc. And I'll do the exact same knurl to the same depth that I did before. Or at least I thought I would. It turns out I can't quite get enough oomph on that thumb wheel to get quite as deep as I did with the nut and the wrench. So I might actually just leave the nut on there and use that instead. But I did the best I could. I did end up with kind of a flat knurl rather than a nice peaky pyramid knurl. This is a perfectly valid knurl. You don't have to go all the way to peaks every time if you don't want. But once again, let's look under the macro lens. Here you can see the difference. So on the right is the new one where the knurl wheels are forced to run in alignment, and you can see the diamonds are nice and symmetrical. And you can see they would have formed nice peaks had I been able to go as deep as I could with the wrench. So that's definitely an improvement. Now, let's try it in steel, because that's the real test of a knurler. This is the same setup once again, same stock diameter, same amount of turns on the nut, although I did do more passes with a smaller adjustment on the nut on each pass. Because this is steel, you got to give it a little more time to form the knurl. At normal viewing distance, that looks like a really nice knurl, certainly pleased with that. But of course, under the macro lens, we can see the truth. The diamonds are nicely symmetrical and they formed nice peaks, so I'm happy with that. There is kind of a general roughness there. You can see some of the peaks are damaged and there's some sloppiness there. That kind of thing is going to be down to a lot of factors. I was probably being a little too aggressive with each pass. The quality of the knurl wheels is going to factor in. The quality of the steel is going to factor in. Whether you're using enough lubrication, all those sorts of things. So knurling is a fairly complex art to get it just perfect. But again, this is the kind of stuff that you really only can see on the macro lens, and I'm generally very happy with that knurl. For finishing, I had intended to cold blue some or all of these parts, but it turns out I ran out of cold blue. I don't have any in stock. So instead I'm going to the Bowshield T9 and I'll leave everything bright finish. When you want to leave things shiny, Bowshield is really great stuff. I've used this stuff for many, many years and I've never seen something rust that's been treated with it. It's basically a form of spray wax. It's got some kind of a solvent in it, so you just spray it on and rub it over the parts and then let them air dry, and then that thing will never rust. It's pretty amazing stuff. It's not cheap, but a little bit goes a very long way. Well, there you have it. That's my new knurling tool, suitable for knurling, or perhaps also for going back in time to warn John Connor about Skynet. This kit is, I think, really great. I had a lot of fun building it. I can definitely recommend you give it a try. It does need a few little tweaks, as you saw, but overall, really a solid kit, and it's a much, much better knurler than the cheap ones that you can buy on Amazon. So thank you very much for watching. I hope you enjoyed this little journey, and I'll see you next time.